Assalamu alaikum. Dear students of standard 11 and 12, how are you? Hope you are fine. Dear students, here you are seeing the picture that is world's number one ranking university, Massachusetts Institute of Technology, that is MIT, and that is your dream university. Today I will take your virtual class in the classroom of this university so that dream can be created in you to read over there. You have to dream before your dreams can come true. Sir APJ Abul Kalam correctly said, dream is not that which you see while sleeping. It is something that does not let you sleep. So let's start the class. This is the classroom of MIT. So welcome to my class. Today's topic, today I will explain you Wheatstone Bridge. Wheatstone Bridge was invented by Samuel Hunter Christie in 1833 and later on it is improved by Sir Charles Wheatstone in 1843. So according to his name, it is named as Wheatstone Bridge and it is used to find out the unknown resistance. This is the circuit of Wheatstone Bridge. If four junctions, look here, four junctions are made due to the formation of a closed loop by connecting four resistors in series, and if an electrical cell is connected between two opposite junctions, then the circuit thus formed is called Wheatstone Bridge. So this is the Wheatstone Bridge which I will go to explain today. Look here, P, Q, R, S are four resistors are connected in the circuit in this connection, and there are four junctions A, B, C, D. Okay, and there is a cell. The cell is connected between the two junctions A and C, and there is a galvanometer which is connected between another two junctions B and D. Thus, Wheatstone Bridge is formed. In this situation, the main current that is supplied by the cell is I at junction A divides into two parts. One is I1 that goes through P and another one is I2 that goes through R. The current that is I1 at point B, again it will divide into two parts because you know from the Kirchhoff's law, Kirchhoff's current law, that current always, when current gets any path, then it will divide. Okay. So when I1 current reaches at point B, then it will divide into two parts, that is Ig that goes along the through the galvanometer, and you know galvanometer is the device when current goes through it, then it shows the deflection. Okay, so Ig goes through galvanometer and I3 goes through Q, and the current that goes through R at this point at point D, reaching at point D, it will go through as a form of I4 through the resistor S and reaches at point C. Then from here I3 and from here I4, then again these two current combined and becomes I and come to the negative end of the battery. Okay, so here look, you can tell me why I1 current divides into two parts and come through the galvanometer. Why not I2? Look, I1 at point B divides into two parts, and Ig is coming through the galvanometer. That's why the current is already coming from one in this direction, so I2 will not go through the galvanometer. Okay, so I2 will go through the resistor S as I4, being I4, because the potential, due to the potential it happens, the potential at point B, we let the potential at point B is greater than the potential at point D. That's why current is coming from B to D, because you know current always flows from high potential to low potential. If we let the potential at point D is greater than the potential at point B, then the current will flow from D to B. So here, whether current through the galvanometer will flow or not depends on the potential at point B and D. If for the resistance the potential at point B and D are not equal, then current will flow through the galvanometer. Okay, because there is a potential difference and potential at B and D are not same, so there should be a potential difference, and the potential at B is greater than that of D, so current always flows from high potential to low potential. So then current will flow through the galvanometer, and the galvanometer will give deflection. This situation is called unbalanced condition. But if the potentials at point B and D are same, then what happens? Then no current will flow through the galvanometer, because you know for flowing of the current there should be a reason, that is there should be a potential difference at the two ends of the conductor. But if the potential at B and D be same, then no current will flow through the galvanometer, and that situation is called balanced condition or null condition. So by controlling different resistance in the circuit, balanced condition is established. Now we will determine the current and potential difference by using Kirchhoff's law and establishment of Wheatstone bridge principle. You already know Kirchhoff's law. So you know Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law is what? Kirchhoff's current law means at any junction the incoming current equal to outgoing current. So at junction B, if we apply Kirchhoff's current law, then look, I1 is the incoming and Ig that goes through galvanometer and I3 that goes through Q are the outgoing current. Okay, so we can write I1 equal to Ig plus I3. Now at point D, if we apply Kirchhoff's current law, then you can see here I2 is incoming and Ig is incoming at point D, and I4 is outgoing. Okay, so according to Kirchhoff's law, we can write here I2 plus Ig equal to I4. It is equation 1 and it is equation 2. Now we will apply Kirchhoff's voltage law in this two loop. Here you can see this is loop 1 and this is loop 2. This is A, B, D, A is one loop and B, C, D, B is another loop. Okay, so at first we will apply Kirchhoff's voltage law in the loop A, B, D, A, and we will measure the potential difference across P, across the galvanometer, across the R, moving clockwise. Okay, so the potential difference across P is the resistor, will be what? You know, V equal to IR. So here will be I1P, and I1 in which direction? We are also measuring the potential difference in that direction, so it will be positive. Then again, when we will move in this way, then IG, the direction of IG and our direction is same, so it will be also positive. So IGG is positive, but here in this way when we go through this, then I1, I2 is in this direction, but we are moving in the opposite direction, so it will be negative. So I2R will be negative. So we will get the equation 3, that is I1P plus IGG minus I2R equal to 0. Now we will apply Kirchhoff's voltage law in the closed loop BCDB. Okay, look, here also we will measure the voltage moving clockwise direction. Okay, look, so I3Q minus I4S, because I4 is in this direction but we are going that direction, so it will be minus. And here also opposite, IG is in this direction but we are moving in the opposite direction, so it will be also negative. So I3Q minus I4S minus IGG equal to 0. Equation 4. So when there will be no flow of current through the galvanometer remains in equilibrium condition, and I said that is balanced condition or null condition. Then Ig equal to 0. Then there will be no flow of current through the galvanometer. That means Ig equal to 0. So if Ig equal to 0, then from equation 1, I think you remember, and I wrote here I1 equal to Ig plus I3. Equation 1. When we apply Kirchhoff's current law at the junction B, I1 equal to Ig plus I3. So it becomes what? It becomes Ig equal to 0. That means I1 equal to I3. And from equation 2 was, look, at the junction D when we apply Kirchhoff's current law, I2 and Ig are incoming current and I4 is outgoing current. So in this equation, if Ig equal to 0, then I2 equal to I4. Okay. So from equation 3 we get what? Equation 3. Do you remember? I1P plus IGG minus I2R equal to 0. It is equation 4. Equation 3. So in this equation, if we put the value of Ig, that is equal to 0 in the null condition, then it becomes I1P equal minus I2R equal to 0, and we can also write I1P equal to I2R in the next equation, next step. So from here we can write I2 by I1 equal to P by R. This is equation 6. And from equation 4, here I have written equation 4 was that I3Q, when we apply Kirchhoff's voltage law in this loop, then we got this equation I3Q minus I4S minus IGG equal to 0. So in this equation, if we put the value of Ig equal to 0, then it becomes I3Q minus I4S equal to 0. Okay. So from here we can write I3Q equal to I4S. Also we can write I4 by I3 equal to Q by S. Equation 7. So from the previous calculation you got I1 equal to I3 and I2 equal to I4. So we can write I2 by I1 also equal to Q by S. Previously we got I2 by I1 equal to P by R. So now if I1 equal to I3 and I2 equal to I4, so in place of this we can write I2 by I1 equal to Q by S. So from equation 6 and 7 we get, look, I2 by I1 equal to P by R, and I4 by I3 equal to Q by S. Again, I2 by I1 equal to also I4 by I3. So we can write P by R equal to Q by S. So from here we can write P by Q equal to R by S. So the ratio of the two resistance in the same order on both sides of the galvanometer will be P by Q equal to R by S. This is the principle of Wheatstone bridge, this formula. Okay, and that's why I kept it in a box, and you should memorize this formula, P by Q equal to R by S. And if you know three of the resistor, and then you can find out the resistance of the fourth arm. Here P by Q equal to R by S. So here AB, BC, CD and DA are respectively first term, second term, third arm and fourth arm of the Wheatstone bridge. Dear students, Wheatstone bridge which I have derived here, this formula, you have to practice it by writing in your copy. After finishing my class, when you will watch the content, you must practice it by writing in your copy. And in the next content, I will give you some mathematics to do, and I will also show how to do those math by applying Wheatstone bridge principle, and that will help you. So today, after this, goodbye everybody.